Okay, it's on YouTube. Done. Okay, so let's go back.
Okay, you could start, Dr. Omid. So thank you everyone for joining us today. And hopefully Dr. Omid answered more questions in the classroom. Okay. And we could start today.
Okay, so I'll start with some of the questions that were posted. Okay, so let's look at Saturday. Okay, so we have Singh is asking how to extract those distribution of multiple fields from different Gantt triangles. The problem is, okay, usually when we do treatment planning, we give from different fields, different MUs, okay? So with the current installation of EGS, all what you can do is just get a distribution of let's say dose distribution from a single field. Now, when you want to add this dose distribution to another dose distribution, it's doable. You can do this, I think, through stat dose. But the problem is then if you have different weights, okay, different MUs. That's what we usually do in radiotherapy. Then how do you weigh these distributions? I don't know. Maybe there is a feature. I haven't done it. I know with the MMCTP, it does it for you. So that Andrew could have actually coded somehow, or it's something in with the stat dose. You can actually give different weights. So the basic idea is that you do a calculation for the separate fields. This is what you need to do, and then you combine the dose distribution. So I would suggest try it with the stat dose, and the simplest thing is you assume that they're equal weight, so the same MUs, or you do it that way. So that's my suggestion. How to simulate those in a patient CT geometry? Okay, this is a CT geometry. I mean, now you have a CT DICOM files. And with those XYZ, all what we know is just a voxels. And in each voxel, we have a medium. For example, water, lung, you can even change the densities and so on. So the question is, how do you convert DICOM files for a patient to a what we call it, egsphant, I think that's the file format, that is usable with EGSnrc. So the steps are the following. I have actually downloaded, I actually brought, so I have, this is a DICOM, these are the DICOM file of a patient. Okay, list of, okay. So here, those are in green. In green, those are just the DICOM files of a patient that we have. We have how many images? So 129 images, okay? What you need to do first is you need to actually create a text file or a file that has the names of these DICOM files, okay? So I will show you, I've done it, okay? TG119, that's my patient, that's my patient name. So this is just a text file that has a list of the DCM files for that particular patient. In Linux, this is very simple to do it. You do, for example, ls, and we pipe this into a file. So I can call this test, for example. So now the ls command lists these files. Okay, maybe I should do it better. Okay. Because I have a bunch of other files actually listed. So I'm going to restrict it. I want only the files with an extension, DCM, and pipe this arrow. When I put this, that means the output, whatever output of that command, put it in a file. And that file name, I'm going to call it test, for example. Okay. So if I look at test, I open it, then I only have the list of the DICOM files for that patient. Okay, maybe there is something similar in Windows. I would suggest, so maybe there is a dir command, and then you can pipe the outcome, the output of that command into a text file. or to a file. I'm not sure. I don't know how to do it with Windows. Maybe there. Otherwise, you just have to copy one by one the file names, and this is very tedious, especially if you have 128, 129 slides. So that's the first thing. So we have this file. I called it test. Okay. More in Linux is just to show the content. So just show me what's the content of that, what's in that file. So these are the list of the DICOM files. The next thing is now we issue the command ctcreate. This is compiled, it should be ready compiled with the EGS system, ctcreate. And when you turn it, when you launch it, you start to get these, unfortunately, there is no GUI for it, okay? It's like the stat-dose thing. So the first thing is here, we need to select what's the format. So in our case, it's a DICOM, so I'm going to put 3. Okay, and then the next line, this is where I put the, you see, it's the, I put the full name of the file, of DICOM file names. So we have generated this, I called it test. Okay, when I do that, it reads the DICOM files, okay, and it extracts the information. So for example, now the information, the X range is from -25 up to 24, -25 to 24, and in the Z direction, it's -16 up to 16, okay? The dimension, obviously, this is the dimension of a CT. It's 512 by 512, and the number of slides are is 129. Okay, now with these directions and coordinates, that's a bit confusing, and I will try to explain this a bit more. Then this is the resolution, okay, of the two of the boxes, okay. Then the next thing is, okay, now I want to generate this phantom for EGS, and I can actually not use everything from the DICOM files. Okay, I can cut it if I want. So this is the minimum and maximum dimensions in the X, Y, Z that I'm interested to actually convert into an X, you know, and just to make things simple, I just take everything. So I would just put -25. Okay, up to this is 25, and then we have for the Y is going to be -25 up to 25, and then for the Z I'm going to put -16 up to 16. Okay, so now it's going to resample the CT data for those XYZ NRC. When we, my version of those XYZ NRC has, I think, 120, I forgot the number of, you know, XYZ boxes, you know, I think I have 128, we can check it. So what you need to do is then, if you want to really get, convert this DICOM into a resolution, into an X file with the resolution that is similar to your CT, we need to modify the dose XYZ file. That's in the macro, users macro. I can show you how to do that. Otherwise, since the number, in my case, the number of voxels in the X, Y, Z directions that's supported currently in my dose XYZ file is actually larger. The number is lower, so the resolution is worse. Okay, so now basically this is the minimum resolution. Although with the CT, the resolution was 0.25, but this is the minimum resolution that I can actually obtain with the dimensions of my dose XYZ. So I'm going to put 0.5, okay, 0.5. So this is the resolution, and then I'm going to put 0.3, okay. Obviously for the Z it was better. We have to look at the dose XYZ. That's the thing, okay. So when I did that, then it's going to actually convert the CT data and generate this phantom with this resolution. The next step is now we need to assign the medium, and this is a very critical step. Okay. The CT data obviously has CT number. So for example, when the CT number is minus 1000, we know this is air. When it's 0, it's water. When it's 200 up to 700, probably that is bone. More than that, maybe it's a metal, okay? And tissue is, So the question is how I'm going to, for example, assign the medium based on the CT number. We could, for example, say anything between minus 100, minus 1000 up to 1000, up to, let's say, minus 700, you immediately give that medium or voxel, you put air there. We could do that. And then from minus 700 up to, let's say, minus 300, then we're going to put lung. So in the CT data, those are the CT numbers. If it falls within that, then the medium assigned to the voxel is going to be lung. And then from minus 300 up to, let's say, 200, we're going to put tissue or water. And then from 200 up to 700, we put bone. And then from bone up to, we can make a material titanium. Those mediums should be in your PEGS data file, okay? So because we are assigning medium, we're going to assume that that is in your PEGS data file. There is going to be another problem. The other problem is, okay, now suppose for tissue, we said for tissue, we're going to assign any CT number between minus 300 up to 200, we're going to give it tissue or water. So, but the density of water is 1. And we know that the density somehow is going to be a function of that CT data. And that's why we need to define what's called the ramp. So for example, we can, okay, I'm just giving you some explanation, okay, is, for example, we can say if the CT number is minus 300, then use water, but the density of the material, you put it at 0.7. You don't use 1, okay? And then you will say at 0, for example, that the density of the material is going to be 1. And then at 200, the density of the material could be 1.05. This is what, it's a ramp. This is how it's done. Okay, and I've seen actually people define different ramps in different ways. It depends also on the number of materials you're going to have in the CT data, CT numbers. Okay. So we can use the simplest way. We can use actually a default, some sort of a ramp function that they have actually, encoded. So if we wanted to use that, so I'm going to put 0 and 0. Okay. But if I want to change, if I want to use a different expand, I think with this ramp, we have 4 media. But if, for example, I decide to use 6 media, okay, then we need to make our custom way. So this is 0 and 0, okay. Then let's look at this. So here, for example, CT number, low. I mean, if I'm not going to use the default one with the system, with this, I need to actually enter these data. So the CT number, the lower bound ramp is minus 1.024. So we expect the CT numbers to be from minus 1000 up to something, okay? So this is basically the lowest value. Medium one is air. And that will go up to, so from minus 1.024 up to minus 974. So if the CT number lies within these two values, please put air for that voxel. And this is the densities. So the density for the lower one, this is the density for minus 1024. We're going to put 0.001. Material is air. And this is the density of when the CT number is at minus 974. Okay, so I'm increasing the density a little bit. Now, the second material is lung. So for lung, we're going to use it from minus 974 because now the maximum of air is going to be the minimum for the lung. Okay, so that up to -724. Okay, so the CT number in range between these two values, that is, I'm going to use material of lung. And the density is going to be the lowest density 0.044, and at -724 the density is going to be -0.302. So if a CT number is between these two values, then just linear interpolation, it determines what's the density of the lung for that. And now for tissue, it will go from -724 up to 101. Okay, and these are the densities. Okay, so I hope it's clear now what's happening, at least the format. And then above that, so from 101 up to 1979, then is going to use bone with this the lower density. So 1.1 is the density at 101 CT number, and it's going to be 2.08 at higher at 1976. And then we could, for example, have titanium or metal, for example, that we take it from there up to different value. Okay, this is different. This is the big advantage. This is the main advantage of Monte Carlo for heterogeneity corrections. In most treatment planning systems, heterogeneity corrections or the dose is actually reported to water. Okay, it's not lung tissue or the doses are reported to water. So let's look at the chat. Are there any questions?
We have one question from Singh. Can we use egsphant to create the RAM function, which has, I suppose, more than 7 different materials?
Yes, you can. But the RAM, this is the material. But you need to actually generate the materials, those materials in your PEGS data file. That's number one. The second thing is then you have to think what is going to, okay, I'm going to use this material from this value of CT up to that value of CT. Because the CAT fan, when you scan that phantom, you have one CT number for that material. But now we have to say, okay, we're going to allow I mean, we need to make a range for it. Okay. So I hope you understand this point. That's why it's left up to you as a user to determine, for example, what is the range or of using that particular material. And then are you going to modify the density, or are you just going to assume the density be constant? So obviously it does not make sense to have a constant density in this case from, let's say, from -724 up to 101, and you just assume tissue with a density of 1. This doesn't make sense. So you need to figure a way how this is done. Okay. Yeah. So once you have so if for example we decided to actually CT create, so if we decided to do it manually, okay, so -25, 25. That's why I love MMCTP. It does everything automatic for me. And then -16 up to 16. Okay. So this I'm going to put 4 or 5. Does not matter. 0.5. Okay. It does not matter. I'm just putting the values. Okay. So if I'm going to so it's calculating the bounds and CT values. Now, if I want to do it manually, I would say, for example, okay, this is number of medium, number of media. Okay, maximum I have 20. Minimum CT number of RAM. So I need to put how many materials I'm going to use. Suppose I'm going to use 6. Okay, and then the minimum CT number I'm going to put, let's say, -1000. So the first medium I'm going to define is this air, for example, 5 to or 700 ICRU. Okay, that's why I don't like doing this, because you need to be careful on typing the names of material. Okay, so that's the material. And then the next step is here. Okay, CT number of upper bound. So we want this to go up to, let's say, minus 900. And then the density of when it is at minus 1000. So I'm going to put like this. And then another comma. This is the density of the upper bound. So I can put 4, for example. Okay. So now I'm going to put the second material, and this is going to be lung, 5 to 1, for example, ICRU. And then we start, because now the lower bound is going to be this, is going to take it from there. So CT number of upper bound, I want to use lung up to which CT number? For example, I'm going to put, let's say, minus 500, just so that I deviate from this, the built-in function or ramp that they have. And then the density, so I'm going to put 0.004 up to 0.25. Okay. Okay, so this means that when the CT number is at minus 500, the material is going to be lung, and the density is going to be 0.25. But if the CT number is at minus, let's say, 600, then it's going to be still going to be lung, but the density is going to probably be lower than this. So it's going to do an interpolation between this value and that value. Okay, and so on. This is how, so now we need to go one medium at a time. Okay. So once we have done this, this is the phantom that, so now because I use test, this is the phantom. Okay. This is test egsphant. What I usually do is I move this phantom into the dose XYZ directory, because when I want to actually display the dose distribution in the dose XYZ show, I need to provide it with two things, with the file that has actually the doses and the file that has the phantom, okay, the name. So, and these need to be in the same directory. I could run the simulation using this file, which is not in the dose XYZ directory, and that is fine. But the problem is if you want to use the dose XYZ show, then they have to be in the same. So I'm going to move it or copy it. Okay. So I'm going to copy this file. Okay. And then I will put it in the dose XYZ directory. Okay. Now we can go and open just dose XYZ and generate a new input file. So we'll go there and start a new input file. I think this is trivial. I mean, this is, now you should be experts on this. So I'm going to use, actually, I'm going to use a different file because it's, I've used their, the default, or, you know, they have generated for me that ramp, which has the material names that is in the 700, it's in this file. Okay. So the only trick, the only thing you need to be aware of is now here, okay? In the past, we were using non-CT data input, and we're defining voxels and groups, and then defining the medium. And then we were generating the egsphant file so that we can show it in the dose XYZ show. We don't need to do this now, okay? Because the egsphant file is already there. So here I'm going to use, okay, I want to use a phantom created from CT data, and then I can actually use or browse, select that phantom. In our case, I'm going to use so did we copy it? It should be there. Test, there it is, okay? Now I have options. For example, do you want it to zero the dose in air? So for example, you have surrounded with your patient information air. Do you want Monte Carlo to display the dose in air because there is dose in air, or you want it to actually zero it? So it's up to you, okay? Dose output, this is something I strongly suggest that you should suppress it, okay? Dose output, dose print, yes. Okay, because then the file, the information, the number of voxels is huge, especially when you're using CT with the resolution of a CT. So that's 512 by 512 by the number of slides. Imagine how many. So we already are storing the data in the 3D dose file, but now you're asking the system to actually also make another output. This is going to be a huge file. So usually I don't use it unless, I mean, you could try it and see if that file that's generated, is it useful or not. So once we have this, then we can then start to think of, okay, what's the source? That's the next step. So let's put here test phantom, okay? And this is the part that is a bit tricky, okay? And I don't know which beam we want to use, so let's use a parallel from the front, okay? Now, in CT data, this is not how the axis or the coordinate system is like. We have the X in this direction and the Y is actually on top to the up there. And then the Z is actually the number of slides. Okay. So the Z is probably going to be this direction. So Z is going to be here, Y is going to be there. And then X is in this direction. But when you do the simulation, okay, this is the coordinate system that you have to think about. So the question then is the beam. If the beam is coming from the top, then the beam needs to be parallel to the y-axis, okay, in the CT data. Is this clear, or should I explain it? Should I draw it on a piece of paper just so that we understand what's going on?
Dr. Omid, this is the default coordinates in the EGS, right?
This is, yes, default with those X, Y, Z.
Okay. Can we change these coordinates or you cannot?
No. Okay. What you need to do is you need to play with the beam direction. That's what you can do. Okay. So for this case, in this, I cannot use this source, or this source is actually useless to change the direction, because the source is going to be actually perpendicular. So imagine, basically what this is saying is that imagine we're talking about a head phantom, okay? So in this direction, the source is going to come from the Z direction. The Z represents the slide, the slides, right? So,
yes.
So that means we have a vertex field. It's not an interior field. It's actually coming vertex.
Yes.
Okay. So this is the problem, and that's why this source is probably not useful. What we need to, okay, so let's cancel this.
Okay. People asking so you to draw it rather than explain if it's
okay. So now I'm going to use a parallel beam from any direction with a rectangular collimator. This is what I need to do, okay? And I'm going to put this as, now I can actually change the source direction to whatever direction I want. Okay. So let's stop this sharing and let's go to the camera. I knew this was coming, so that's why I had to prepare the camera. Okay. Okay. So for example, I'm going to talk about, let's say, our eclipse. I know about eclipse. Eclipse, what we have? We have the slides are like this, okay? And then this is the third slide, okay, like that, okay? This is actually the Z-axis in eclipse. And within a slide, this is actually the X-axis, and this is the Y-axis. Okay, so the Z-axis, because we need to use the right, so the Z-axis, the Z coordinate is actually going to be like this. Okay, because X cross Y should give me Z. That's how it is. Okay. Clear?
Yeah.
This is an eclipse, right?
Yes.
So now I want actually a field. Suppose I want the field to come anterior from there, okay, from that direction. That field, okay, this is my field. The field needs to be parallel to the Y.
Yes.
Make sense?
So, yeah, makes sense.
Okay. And if Y is in that direction, is actually opposite to the Y. It's in 180
Minus direction.
right?
Yeah.
Opposite direction, right?
Exactly. Yes.
Okay. So now the problem I have is that those X, Y, Z, this is eclipse. Okay. And we have here those X, Y, Z. Okay. What is the coordinate system? The conventional way is that we have, this is, okay, I have, okay, these are like that. These slides are not the same as these. Don't confuse. I'm just showing you what's the coordinate system there. So the coordinate system is based on eclipse. I just want to open it so that I may draw it right. Okay. So based on eclipse, the coordinate system, this is, the Z is actually this direction, okay? And the X is here, and the Y is there. So the Y is this Z.
Yeah.
Okay. Okay. I just want to make sure that you can see my camera. Okay. Okay. So this is the Z. This is the Y. So X times X cross Y. I'm just trying to think, is Z up there or opposite? It should be, oh, okay. That's a bit confusing to me. Okay. Yeah, but this is the coordinate system that they have. Okay. For now, when we put the patient, okay, the X, Y, Z, the patient, this is not the direction of the anterior. Okay. No, the direction of anterior is this. This is the anterior view. Okay. Because with eclipse, it's, this is the Y direction. This is your anterior. Okay. Then anterior is like that. So as if the patient is actually lying like this. Okay, as if the patient is like that, and this is your, or I don't know how to draw it properly, but it's a bit different. Okay, so this is the confusing part, and you have to be careful about it. Otherwise, you run the simulation and you think, okay, I'm shooting the beam from top, but I don't see anything in the patient because your beam direction is wrong. It's shooting outside of the patient. So let's go back and go and look at, okay, share. Okay. So this is now the coordinate system, okay, of the dose XYZ. What we need to do, we need to have the beam. So this is the positive, okay. This is X. The beam has to actually come from this direction. I think it should shoot this way. Okay. We need to somehow rotate this beam so that it's shooting this way. This is the anterior part. So when we enter, okay, the coordinate of the isocenter, we can put this to be, suppose this is in the middle of the phantom. I'm going to put the 0.000, okay? And the theta, so we look at the help, okay? And the theta is the direction, is the angle between the beam and the Z axis, okay? So I want this beam to come from here. So the theta is going to be 90 degrees. So theta is going to be 90. Now, and the phi, so here, these are explaining, or from the drawing. The phi is the direction of or the angle between the axis of the field and the x-axis. Okay, so I want this to be, I think, minus 90 degrees. Okay, so this is going to be at minus 90. Then the width of the beam, I can put this to be 10, for example, 10, because this is a rectangular shape. And collimator, I want this to be 0. And we can put here, for example, we have, let's do electrons. So let's do 12. And so here, let's do electrons. Of course, we have to check the physics. So this, the default is this. The rest I'm gonna leave it. So this is the only part that is confusing. And it took me a while. I was trying this yesterday, and I think those are the angles that then I start to see those actually. It's not trivial even for me because I don't use this a lot. So there we can save the input file as test. So let's run it to see if everything is okay. So it ran. Okay. These are 100 particles. Okay, not a lot. Okay. And so let's go to our those X, and then we put those X, Y, Z show, and we have test. Okay, probably there is nothing. Yeah, probably there is nothing yet. I don't know if it's because of my direction, but this is the phantom, just to show you my phantom. Okay, it's based on CT data. This is a phantom, solid water phantom that we use for IMRT. We use it actually for TG119 commissioning. It's a solid water, and let me show you a different plane. So you can see the couch. Okay, and we should have somewhere the chamber, opening for the chamber. I don't know, maybe because of my resolution with this phantom, I selected something. Yeah, there it is. Okay, so that is actually where my chamber goes. We tried this. See if there it is. Okay. Okay, and of course we have 100 particles, but I ran a simulation. Okay, and let me show you what I got. Those X show TG119, TG119. Okay, I thought I actually ran this. Oh, okay, so there is, yes, okay. I used a beam source, TG119. I have electrons somewhere. Probably I don't, okay. TG119. And yes. Okay. Okay. So this is, I'm using this is actually a square field. It's a 10 by 10, but it's just the scale is a bit different in these two axes. So this goes up to minus 25 to 20, minus 25 to 25. This goes to minus 16 up to 16. Okay. This is how it looks like. Okay. Of course, when I ran this simulation, I told the system, look, air, report anything in air to be 0. Don't report those there. That's why I'm getting this. Otherwise, I would have actually gotten those in this area here. This is what's happening here. This is not air. The CT number of the couch is probably not, it's a bit high, so it's not air, and that's why it's reporting those in here and here. Okay, but beyond that, there is no dose. Okay, now let's look at just the input file. I think I did one for electrons. I just don't know where is LSTG119. Okay, this is beam source, beam source. Is that for electrons? Let's try to see if. Okay. Yes, I think this one is electrons. I just don't know why I'm not getting any doses here. Yeah, there it is. Okay. So this is for an electron beam. Okay, and I think it's 12 MeV, and this is the dose distribution you have in the phantom. Okay. So now let me just go and open the file so that we look at the directions. We look at edit parameters. So let's load the previous input file. Yes, and we're using this one. Okay. So the beam source is actually the Linux model that we have been building for the 15 MV. I use it as a beam source and run the simulation. So here, this is a parallel beam from any direction with rectangular collimator, and that's number one. And this is it, 0, 0, 0, and 90, minus 90, and 10 and 10. Of course, this is fine. This, you could use this. I mean, this is not at 100 SSD, but it does. But actually, the results are for 100 SSD setup for electrons, because I'm using just a parallel beam, shoot from top, and that's it. Okay. If I was using a point source, then I would need to be careful. Where is the isocenter, and I need to take care of this. Now, for the beam source, okay, that's an isocentric treatment. Icocenter is actually in the middle of the chamber. And what I've done, so that you understand how to do this, is edit parameters, load the previous input file, and we will open the beam source. This is wrong. Load the previous input file. Yes, discarded. I want this one, beam source. Yes. So now I have treatment head simulation. Again, the direction is 90 and minus 90 because it's an anterior field. But the input file for the beam model, I'm actually generating a phase space file at 70 centimeters. If you want to do isocentric calculations, it does not make sense that you generate your phase space file at 100. So the air in the Linux, I can go and show you, I made it up to 70. So that is roughly the phase space file just after it exits from the window of a Linux. Then I can put the phantom, the coordinates for the phantom, the 0, 0, 0, when we did this, or when we were doing our measurements, we placed the isocenter at the chamber. So I just need to make sure that this is correct. And then I run the simulation. So the phase space file is actually at 70, and the chamber is at 0, 0, 0, and that's it. So here is the distance. So this is the distance from the source. The phase space file is 30 centimeters from the isocenter. That's why I put here 30. Okay. So it's not trivial, but you need to do this. I mean, you need to figure out these geometries and so on. I've never done it. I never actually calculated with with AGS directly doses in a phantom, in a CT phantom. I have never done it, but I did it through MMCTP because everything is nicely made.
Dr. Omid, how many number of histories have you been using to achieve this?
This
9 million?
one, this is for photons. It's 10 million.
10 million.
Okay, because I know it's the way I do the simulations, I do 1 million. Okay, so that's the first run, and then I change it to restart, and I add, for example, the 10. I want it to be 100 million. Then I add 9 million. Now the next step, if I want to improve the uncertainties, then I would go, for example, for 100 million. So here I just need to keep everything as restart and add a zero, and that's it. Okay. So this is how I do it. Okay. So I think this is up to 10 million. Okay. And with beam simulation, it takes a bit time. With the Triton head simulation, it takes time. But for electrons, the electrons was very, very nice. And let's go and open it if you're interested. Go the previous input file. This is for electrons. Okay. And you see, I managed to do this with probably 3 million or something like this. Okay. And we have a very good distribution.
But if you have the iWatch output enabled, then it will take much more time, right?
No, iWatch, you should not use that. Okay. No, you should not watch it in any simulation. iWatch is basically generates a file that has the track histories of the particle. So for example, you have it actually record, we have electron number 1. It was at this position, and then at that position, at that position. It will actually, for the interactions, because that file is actually used by a different program, by X Windows, in order to draw the tracks of the particle.
Okay.
And then it does not make sense that you actually want to keep history of 10 billion track of particles.
Yes,
the
right.
program is going to crash.
Yeah.
So usually, what people do is, for example, at most, they will actually, and I think even the program, when you open, when you open X Windows, if you have more than 300 or 100 histories, it will not track them. It will just track the first 300 particles, something like this. Okay. Because otherwise, so never use iWatch. Okay. Don't use that. Okay. So I think this explains CT, and you see how confusing it is. Okay. Okay.
We have 3 questions.
Okay,
how these histories are related in the shared library.
What do you mean shared library? I mean, I don't know what you're talking about.
Chand, can you talk, please?
Hi, Dr. Rahman, can you hear me?
Yes.
Yeah. Actually, I want to ask you this, like when we define a LINAC in the beam, so we have certain number of histories there also, and then we make it as a library, and then we do all the simulation from dose XYZ. So there also we are giving certain number of histories. So how these two files are related in term of number of histories?
Well, everything is dictated by the number of histories in your dose XYZ. Okay, the point is, or in dose RZ. For example, we want 100 histories. What it does, it will go and run the LINAC head simulation and get one history, get a particle from there, an outcome, and then use that particle in the dose XYZ. So in the dose XYZ, how many particles do we need? We need 1,000 particles. Okay, then it has to do this 1,000 times. Okay.
So it is like that only, that the number of histories in dose XYZ are getting simulated from the beam and then to dose XYZ.
Yes. Okay. So basically, it's asking. It's like a phase space file. Dose XYZ wants a particle, wants 1,000 particles, for example. Okay. If we have this in a phase space file, it will read the first 1,000 particles, end of story, and simulate. But it does not have a phase space file. It needs that from the LINAC head simulation. So then it will actually get them from the LINAC, simulate them from the LINAC head, and then it will track them in the dose XYZ.
Okay, so please continue.
Go ahead. Yeah.
Yeah, actually, my concern is like if I have given certain number of histories, say when we define an EGS input file, so it has by default say 100 number of histories. So does it take that also in account in any way, or it is directly taking the number of histories what we give in those XYZ NRC?
It's from those XY. So for example, you can put actually in the input, let's say an input file of a beam source, right? You
Yeah.
could put 100, you could put 100, you could put 10 million. It does not matter.
Okay.
Okay. It does not matter. Everything will be dictated with those XYZ.
Okay. Okay.
Okay. So that's,
Thank you.
yeah. Okay. So please, do we need to get physical histories or it is computer generated? I don't know what does this mean? Physical histories. What's physical history?
I mean, maybe he is asking, do we need to put the histories by ourselves or it's generated by the computer? Yes, for sure. You have to put it by yourself. You define how number of histories you are looking for. It's not generated by the computer. Yes.
The number of histories. If he's talking about the number of histories, yes.
Yeah.
Because we have to put it, you know, and we have to actually tell in the input file, is this going to be a restart? This is an advantage of EGS, is that you can always restart simulation. So now, for example, I've ran the simulation 10 million and statistically it's not good. I need to add more, so I can restart. With restart, it will actually accumulate more histories. Okay, it's not going to, it's not going to erase what has been done. No, it's just going to actually accumulate more histories.
Can you please explain why 70 centimeter is chosen for scoring phase space file? Can we score different distances like 75, 80, 85?
You can score at any distance. In a LINAC, okay, think you use a cobalt machine. That's a bit different. 80. In a LINAC, the isocenter is at 100. We know this. But the question is, when we treat patients, for example, we don't, usually we use isocentric treatments. So the distance to this patient surface is not going to be 100. It's going to be 70. 70, that's too much. Okay, probably it's going to be 80, 95, right? Depends on where is my center placed in the patient. That's why what we do is, if I want to use phase space files, it does not make sense I produce the phase space file at 100. It's wrong. You produce it at 70 centimeters. And you use that phase space file now to track it in the patient. Then you can play with the position of where is the eye center, patient eye center. You know, you can do that. You can play with the patient. That's why you do it at 70. You could do it just after the exit window. I selected 70, just, you know, that's it. But you could actually put it at 65. 65, probably that's at the exit window, I think, for our Variant machines. But it's just something outside of and usually people sometimes 70, because if they're having a wedge, probably that can accommodate it. I'm not sure. Okay. But anyway, you need to score the phase space file at a different distance. Especially now when we're doing the optimization of our LINAC, I could actually score it at 70 and then place the phantom at 100 and tell the system anything between 70 and my phantom is air. We can do that, no problem. Okay. Or what I tend to do is I actually score the phase space file at 100, and then in the dose XYZ, directly this phase space file is above the phantom. I don't need that air layer. So that's the difference. Okay. Can you please explain why 7? Okay, that is done. Any other questions related to this? So for your cobalt machine, what you could do is look at, for example, where is 80 is at your isocenter. That's probably not a good place, especially if you're doing this for patients. You know, you're going to get the phase space file and transport it to patients. Then you put it at a different distance. That should be at the exit of you know, your LINAC. Okay, so probably that's going to be 60 or something. I'm not sure with a cobalt machine. Okay. Anything else? Okay, so the next question is how to verify the energy of the beam using phantom measurement at different depths. You have a PDD that you have measured. You have that. Then what you need to do is with the simulation, you extract, let's say dose XYZ, you extract the profiles using stat dose, and then normalize to 3 centimeters or any distance, and then do a comparison. You have done it. You have done it very well. My only objection was that actually in the statistics or in the uncertainties or the variation that I think you should report everything relative to Dmax. So just take the difference in the PDDs. That is what's good for me. And you need to do this also for the profiles. Okay. Okay, Bilal Hussein, please. Okay, X++ is something I'm not familiar with. I read about it, and it will require people to actually do this through a input file where you have to actually put. It's a bit different than the regular, but more powerful, to tell you the truth. Okay, so I'm going to postpone this till later, so that I want to look into it more. But it's not that difficult, and it's not simple. So we're going to postpone that. And I'm waiting. Luqman around? Luqman actually took a course on this. If anyone took a course on this and he wants to present it, just let us know. And the floor is all yours. We have no problem with that, because I'm keen actually to learn how to
Luqman is not here.
Yeah, to use it. Otherwise, I think the documentation, one can do it through the documentation. It's just that, the way how you're defining your phantom, the medium, it's the same concept. We need to define a geometry. We need to define the medium. We need to define the input parameters, okay, or the control of the simulation, using spin, exact, or, these things. And we need to define what is the output. So do we want doses? We want to, so it's not that difficult. Okay. And for treatment head simulation, Bilal, that is a bit difficult. I'm not saying it's impossible, but I prefer for treatment head simulations is use the beam. It's actually very powerful. But with the X++, you need to define the geometry. You need to define what's the shape of a flattening filter, for example, or the shape of slabs, or even a phantom. You need, and it has those tools. But I would not recommend that you do a treatment head with X++. Okay, now, okay, the Raspberry Pi, I will leave it for now. Okay, I don't know them. Okay. Okay, any other questions or? Okay. If there are no more questions, I want to show you two things. But okay, Hassan, you have a question? Or that's a plus? Just take the mic and state.
This is a long time ago. He's just thinking, okay.
Okay. Okay. Okay, so I gave you a task, an assignment on, for example, about the dose to water, the equivalent depth. That's something, equivalent depth of solid water to water. Okay, usually we tell the density is 1.036. So we say 10 centimeters of water is equivalent to 9.6 centimeters.
Yes.
9.6. Okay,
yes.
9.6 something. The question is this true or not? That's basically what I've asked. Okay, and to see if this is true or not, all what you need to do is you look into the dose in water, let's say at 10 centimeter depth, and you compare that to dose to water in solid water. Okay, solid water and water in terms of doses, they're not the same. Okay. But what we're trying to look for is, let me just explain this on the camera. I think I touched on it last time. Okay. So the idea I have, this is water. And we have, this is at 10 centimeter. Okay. This is water. Now, I want to compare this to those in solid water. This is solid water. But this small voxel or medium, this has to be water, H2O. Okay? Because the reason is your chamber, you have a factor. That factor is a conversion factor that gives you dose to water, not dose to the medium, dose to water, specifically dose to water. So if you put the chamber here and you take your reading and you multiply it by your NDW, corrected for KQ or whatever, okay, that gives you dose to water. So what you have done basically is you have removed the chamber and replaced it by a small medium of water in that place. That small medium of water is surrounded by solid water. So the question is, for the equivalent depth, this depth X, what is this depth X such that the dose in that volume of water here and at 10 centimeter water are the same? Okay. So when you use the density, yes, basically your assumption is that, okay, because of the density, the attenuation is going to be more. So I need to actually, so if this point is at 10 centimeter depth, then the beam is actually going to be attenuated more than in water because solid water is denser. Okay, that's why people tend to, okay, I'm going to shift it. I'm going to put it actually at 9.6. But my argument is when you do this, your point is actually now closer to the source. So although you have accounted for attenuation, okay, maybe you account for attenuation, I'm not sure, but then the point is actually closer to the source. So how to solve this problem, or just how to understand, or how to determine is this true or not? And the reason, or I've done it. So we just, okay, I hope this is something basic, okay? It's just to show you that, how could we use Monte Carlo to look into, to determine, to answer these questions. Where is my Monte? Okay. So this is what I've done. So I use the dose RZ, it's faster. And or actually, let's open it so that you can see the phantom. So we're going here, okay, and I have this is solid. No, I don't want this. I want water H2O, 10 centimeter. Okay. So I've made the geometry. The geometry, I'm not going to explain that. I think now you know this. So I've made actually three slabs because I'm interested in answering one question. Is the dose at this? So I'm going to just plot properties. I'm going to increase this. Apply. Okay. And probably I'm going to increase this. Okay. So what I've done, I use an RZ geometry. Okay. One slab up to 9.95. This is at 9.95. And then the next one is at 10.05. So this thickness is going to be 1 millimeter. Okay. And in the radius is 5 millimeters also. So here, this is the thickness of that particular. So this now, the center of this slab is at 10 centimeter. And it has a radius of 0.5. I could reduce the radius to 0.25 so that we have a diameter of 0.5. It does not matter. Now, I ran the simulation. This is in water, okay? And we can go and look at, so it's H2O, and then this DD5, okay? So this is an output. So at 10 centimeter, this was the dose per fluence, okay? 2.87, 10 to the power minus 12, and with this uncertainty. Now, the next step is I went and made a, this is it, okay? And we looked at, let's look at the preview. Okay, I hope now it's clear, or it's actually, you can see the difference. See what I have done. I'm gonna put this on zero. Okay. So again, this is water, but that particular layer, that particular region, sorry, this is solid water. So in red here, this is solid water. And then in blue, this thing is water. And in this case, this is going to be at 9.6. The center of this region in the Z direction is at 9.6. Okay. And I did another one at 10. So this is at 10. Preview and plot properties. Okay. Again, this is at 10 centimeters, or the center of this is actually at 10 centimeters. Okay, chat, anything? Okay, no, I have a different, I disagree with you, Bilal. Okay, so Bilal said, look, why do we need to put water within solid water, as Monte Carlo is capable of calculating in the medium itself? Moreover, this is only relative calculation. No NDW is required. If you're doing PDDs, I have no problem. So because the conversion from those to water, to solid water, you need the stopping power ratios, and that will be applied. That's, we assume for photons, this is actually constant. So it does not matter. Then we can just put, you know, phantom of solid water, and I agree if we're doing relative. If I want to, for example, state the percentage of those in solid water and water, they're equivalent. I have no issue with this. My issue is when you start to say, okay, the equivalent depth in solid water is 9.6. What do we mean? What do you mean by equivalent depth? Equivalent depth to me is basically a depth. If you did a measurement there, it's the same. It will give you the same dose if you actually measure in water at 10 centimeters. So to be consistent, then I'm going to put water and water here. That's what I'm trying to do. Okay, because does 9.6 attenuate the beam or gives you the same dose in water if you actually put 10 centimeters of water or not? This is what I want to actually establish. Okay, so that's why I have to do it this way. And I ran the simulations, and let me show you the results. So here, this is actually, here is the number of histories. So just number of histories. Okay. So number of histories, I did 10 million. By the way, I'm using a cobalt source, so that I'm using cobalt, and I'm using a point source at, I think 80 centimeters, 5 centimeter radius or something like this. I'm keeping, it's exactly the same source, no difference, and the same SSD. Okay. So I ran the simulation. This is in the full water phantom, 10 centimeter. These are the doses, and this is the uncertainty. So I'm just showing you as an example because I feel sometimes people how to look into these uncertainties and how to analyze the data. I think I just wanted to show an example. So here, this is the dose 2.82 after 10 million histories with this the uncertainty. So I divided this by that. This is around a 4% uncertainty in whatever in the dose value. Now, if I increase that to 10 million, to 100, this is 10 million, this is 100 million, okay? So the dose, roughly, not much difference, 2.90, but the uncertainty actually got better or lower. So this is about 1.25%. And this is 1 billion. This is the dose. You see the dose is not much changing. Okay, but what we're doing is we are reducing the uncertainties. And now I could get an uncertainty of 0.4%. Okay, Bilal Hussein, I ran the simulation too, but I got the equivalent is 9.9 for 10 million histories. We said, okay, let's look at our result. Let's look at my results. Okay, and I don't know if you have done it for cobalt or for a different beam, but this is for cobalt. Now, for solid water, this is now the dose in water at 9.6. And this is the dose. And this is the uncertainty. So after 10 million, I got 3.9%. Okay. And you see, as I'm increasing the number of histories, this is not changing much, but I'm reducing the uncertainties because this is important in our case. So the next step is I'm going to take this dose value divided by the dose in water. So this is in this column here. So I have 1.04%, but the uncertainty on that ratio, because we also have to, okay, take the uncertainty into account. So the uncertainty, this is how we calculate it. We add, the uncertainties in a way, and I get an overall of 5.61%. Okay. So basically, this is the ratio with a plus or minus 0.058. Remember, equivalent means this ratio is 1. This is what we want. Is it 1 or no? Okay. So I could not tell actually, okay, because the uncertainty is actually, 1 is valid. It's within the uncertainty of what I've calculated. That's why I ran this simulation to 100 million and 10 to 1 billion. So if this is the results for 100 million, this is the value or the ratio 1.021, okay? And now this is within 0.018, so that's plus or minus. And for 1 billion, I get 1.024, so it's 2.5%, okay? And the uncertainty is 0.006. So the uncertainty is very low now. This definitely I can say is statistically that at 9.6, the dose in solid water is not equivalent to the dose at 10 centimeter for cobalt. Because I have to be specific. I don't know if this result is going to be the same if I change the beam energy, use the 6 MV or 15 MV. I really don't know. Okay, that someone else could actually add to this table. Okay, so based on this, I can say confidently say that, okay, 9.6 for cobalt, that's not equivalent. Okay, because the ratio is not 1. I want this ratio to be 1. I ran the simulation. Now the second simulation is solid water, but now I move that water slab or volume to 10 centimeters. So it's 10 equivalent to 10 or no. Then I ran the simulation. These are the doses, water in solid water, but the water is at 10 centimeter, okay, and so on. And this is the ratio, okay. So the bottom line is that when I had the 1 billion simulations, then I have an agreement with what Bilal Hussein said. It's roughly at 9.9, and this is it. So the ratio is 1. Okay, so the equivalent is at 10 centimeters. Now, is this the same case when we use 6 MV? I really don't know. 10 MV, 15, I really don't know. We need to run the simulation with the same concept. That take those in water are surrounded by solid water. Okay, so there is, yes, the attenuation is different. So at 10 centimeter, I don't have an inverse square problem. The attenuation is a bit different, but somehow this might be actually compensated by scattering things, in solid water. And another thing, maybe this is actually field size dependent. So for example, I've used a 10 or equivalent, let's say, to a 10 by 10. Suppose I went for a smaller beam to 2 by 2. Are they going to be the same? Because now my claim is that, yes, the attenuation, we're attenuating, but it's compensated by some scattering. The scattering in solid water is more, or compensates this reduction in primary dose or primary photons. The question is, okay, if I want to actually validate that, then I would actually reduce the field and do the simulation again. If for smaller fields, I get a difference, then probably it's the scattering that is making things to look very nice, at 10 centimeters. Okay.
Dr. Omid, I have 2 questions here. What if we make it, you use the ion chamber in the middle of the field, right? In the central axis.
Yes.
What if you been off axis, let's say 5 centimeters off axis from your field? So now I think the situation will be worse, right?
But you have a large field.
Okay. No, your field is 10 by 10, and you are not isocentric. You are 5 off center.
No, but off center by how much?
Let's say 5 centimeters.
But 5 centimeters will be at the edge of the field, right?
Yes, yes.
That is even worse, that is because now you're doing, it's a penumbra.
In the penumbra region.
I don't know. But I'm trying to answer the simplest question. This is how you tackle Monte Carlo. You go with the simplest question. You try to answer that. Once you understand what's going on, then you start to investigate to see for more complex issues. Yeah.
And what if it is electrons rather than photons?
Electrons, you have to investigate. I don't know. Okay. So what you need to do, okay, but what you need to do, I think for electrons, I mean, you have to look at 2 things. You have to look at the relative PDDs. Are they the same or different? And you have to also look into the dose. And I think for electrons is a bit different. Okay, because if I remember correctly, the TRS 398 allows actually using of phantoms. Okay. Other than water, and they give a correction factor. They give you a correction factor for that phantom. I haven't done it because usually I do the TRS in water, but I think it actually has a section that if a user actually wants to calibrate the beam in polystyrene or solid water, it gives you actually a correction factor. And those correction factors, how do you think people obtained it? It's through Monte Carlo.
Monte Carlo, yes.
This is exactly what they do.
Yeah.
Okay.
Okay.
Okay. So, okay. By this method, can we calculate water equivalence of shield? Look, shielding. You could. I don't see why not. But the problem is then, okay. In our situation, we had water and surrounded by solid water. Now, when we have this shielding material, is this a solid water or water in a phantom surrounded by copper, for example? I don't think so. then the problem will be, okay, where is this copper actually placed to my point of interest? Is it at, you could investigate that. For example, if copper is placed, let's say 1 centimeter above my point of interest, does that have a different effect if I actually use the same thickness of copper, but it's actually 5 centimeters away? We don't know. Because we're not talking just about primary, we're talking also about the scattering, what's happening. Okay. And of course, we're assuming that the copper is infinitely large and so on. So you have to, I mean, we cannot conclude, I mean, because our practices, we don't use copper in a patient, okay, in a phantom. It's something we place away, so just to attenuate the beam, okay? But you know, with Monte Carlo, you can investigate whatever geometry you want. This is the beauty of it. This is the strength of it, okay? So I don't know if that method actually gives you an equivalence of shielding. I don't know. Okay, clear? See, it was simple, and I wish someone to actually do this now for a 15 MV, for example. Do it for a different phantom, different material, PMMA, lucite, okay, or polystyrene. Maybe we can do it, but this is the same concept. Investigate, you know, with different field sizes. So now I've done it for cobalt, but now let's do it for a small field, a large field. Is there a difference, or the same? Okay. Okay, anything else? Okay. Okay, the last thing I'm going to show you, and this is...
There is one question, Dr. Omid.
Okay, yeah, go ahead.
From Sync. How can we continue with the interrupted simulation in between due to power off the system or electricity problems?
Yeah, you need to actually, okay, this is something, it's a bit of work. If the simulation has been like at the beginning, I would suggest you just restart it. But if you have done a lot of, it depends on okay, CD. Okay. Oh yeah, I mean those. Okay, maybe I have it here. LS minus LA. See. Okay. So now these are questions for power users who they want to. Now, when a simulation is done, okay, especially when you do it with parallel processing, usually it's going to be done in the background. Actually, a file is created. Sorry, a directory, a folder is created for a run. Okay, and in that folder, so if I go, let's look at one folder. 47265. Okay. No, I don't know. CD 47266. Okay. So in that folder, you're going to find the EGSdat or the data files. So for those XYZ, the 3D dose file is actually going to be inside this folder. Until the simulation is actually done, then it will be copied to the main directory. So if we go and look at it's this file, I think the par-dose file, that is actually inside, will be stored in those folders until the simulation is done. Then it will be copied back to the main folder. So if you had a power shutdown, okay, what you need to do is then you need to go to these folders, inside them, it's a bit sometimes confusing because sometimes I restart and obviously I don't do like 40 submissions here. But you can figure out, for example, the date when this was launched or when this happened, and then you go inside and copy back the files into the main folder, and then you can restart the simulation. So that it needs a bit of playing around with this, but that's how you do it. For 7, let's see if I have one at 8.164. Okay, it has been copied outside. So for example, I know from the title, this was for TG119. That's my input file, and this is W6 is the splitting the file number 6. So there should have been more files, I think, here, or maybe they were stored actually in the original directory. I'm not sure usually. I'm really not sure, but you need to actually go into these folders and take out relevant files, and then you can resume. Okay. Okay, so we have half an hour. I will show what I've done. I have a Raspberry Pi. Actually, I have 3 of them. I have 2. Those are Raspberry Pi 4. And the third one is a Raspberry Pi 3. It's an older model. And I've actually, they are actually in the network in my house, connected, and they are operating as a cluster. So I went and did some benchmarking just to show you that, and you can tell me, is it worth it or not? So let's go back. CD, okay. Okay, SSH. Pi. Right. So now I'm logging to the Raspberry Pi. It has Raspberry. So now I'm on actually that Raspberry Pi 01. I have 3 of them. Okay. And I ran the simulation for benchmarking just to show you. I'm not sure. That's a GPUs. I'm not sure. EGS does not by default run the simulations on GPUs. But I know someone, or actually I listened to a talk. Someone did something very crazy. He went and got GPU cards. I think those from Sony PlayStations, old ones, and he configured to run EGS actually on these GPUs, and the simulation was really fast. So maybe it is published somewhere, and then you can contact them and see how they did it. Okay, so I ran with the those XYZ, those RZ. There is this default file, the template that comes with it, and I just made copies of these templates so that I can run exactly the same file on different machines, just so that I can do benchmarking. I ran it on Raspberry Pi 4. I ran it on a Raspberry Pi 3, and I ran it on my virtual machine in my Mac. Okay? I did not run it actually in a computer at the hospital, but maybe I can do that. So here, these are the results. So I can show you, for example, and I think I've ran it, I made the number of histories 1 million. So that I can actually, so Raspberry Pi 1. Yes, so that is 01. And then we have the eggs log. Okay, so this is the log file, because I want to know how long did it take to actually simulate. So the number of, does it show here somewhere? I just want you to trust me on this. It's probably written somewhere. I've used 1 million histories. Okay. So 1 million histories, it ran this in elapsed time in about 1800 seconds. Okay, so roughly it's about half an hour. 1 million. Now, for the Raspberry Pi, this is Raspberry Pi 4. Okay, this for the Raspberry Pi 3. Okay, the same file, the same, everything the same, but now it took 4,000 seconds. So it took more than double the time. Okay, it has a less powerful CPU. Now, let's look at the same thing in my CD, and then those are set. Okay. Okay, so this is on my virtual machine on my Mac. So this is one CPU. Okay, I'm not doing parallel processing. Okay. Okay, and it took about 600 seconds. So to do the okay. So the Raspberry Pi 4, actually it's 4 times, or let's say 3 times slower than my actually virtual machine on my Mac. Now my virtual machine, I can actually split this into 8. So basically a Raspberry Pi has 4 cores. So 3 cores is equivalent to 1 core on my virtual machine. I have 8 cores. That means I would need 24 cores, Raspberry Pi, and that means I will need 6 Raspberry Pis to actually be equivalent to my computer. But now, of course, 6 Raspberry Pis, how can I then operate them as a cluster? Okay. So so I've actually installed a cluster, or it's I made them as a cluster, and I'm running something called Slurm. This is a distribution. It's a manager. Basically, you submit jobs to this Slurm. I think it stands for Simple Linux Utilization of Resources and so on. Okay. You submit it to Slurm. And then Slurm, you define, for example, I have, let's say, 3 Raspberry Pis. Each one has 4 cores. So I defined in Slurm, okay, you can actually run 4 jobs on each. These are available. So when I do the submit to Slurm, I'm going to split to 12. So Slurm knows that there are 12 jobs. Then it will see where is which cores are available, and we'll submit actually the jobs and to be run there. Now, in order for this to work, you need to do some networking and Docker and Ubuntu cluster Ubuntu machines and stuff. You can do it with Ubuntu. I mean, I just use the Raspberry Pi because I've actually done it in the clinic with Ubuntu machines. It's running there in the hospital and in the office. But home, I'm just doing it. And in the office, I have access to 4 powerful machines, each one with 12 cores. So I can actually split the jobs into 48. But there is an issue. I face an issue. And these things, when you're actually building your network, you have to be aware of that. So let me just show you how this works okay, so now let's actually submit exactly. So I'm going to copy, let's say the Raspberry 01. Okay, I'm going to put this Raspberry, and then I'm going to do parallel processing, Slurm. Okay, since that's what I'm doing. I just want to make sure that I have 1 million particles. Okay. So this is first, and so it's actually 10 million. Okay, 10 million particles. Yeah, 10 million. It's not 1 million. 10 million. So now I'm going to actually submit this. So what we usually do is we do EXB. Everything is going to be the same, those XYZ, NRC, and then the input file, and then the PEGS data file, which is, in this case, it was Phantom, I think. Let me just, I will just want to make sure that everything is fine. So it's going to run. Yes, it's running. Okay, so EXB. Okay. And what we used to do is we say P equals to, for example, the set number. I'm going to put 12. But if I do it this way, then it's going to launch on this Raspberry Pi number 1 with 12 jobs. And there is no advantage because there are only 4. So each job is going to actually be running with 1/4 of the CPU or 1/3. Okay. So what we do is we define something in the queues. You can have a name for a queue partition, they call it long, short, and so on. And then I tell it batch equals to slur. Okay. So when we do this, now it's going to actually, it's not submitting to the AT, it's going to submit to this Slurm management queuing system. Okay, so we have 12 jobs. Now I can actually see what's happening. There is a command SQ. Okay, so here, this is actually to that management job is saying, okay, I've taken 4. Actually, they're running on Raspberry Pi 1. So it's R running. Raspberry Pi 2, another 4. And Raspberry Pi 3, another 4. Now, if I do top on my machine, you will find it's actually, it only has 4 jobs running. Okay. If I go to second Raspberry Pi, okay, now therefore I'm actually a different Raspberry Pi. So it's Raspberry Pi 2, okay. And then I can go to my third one. The third one is actually the worst, it's the slowest. But now with parallel processing, it does it in a smart way. So it actually takes advantage of, of the faster machines. It will actually ask it to do more particles than in the slowest machines. So that relative, in the past, parallel processing done with EGS was, it just splits, for example, 12. Now I did the split number to 12. It will actually make 12 jobs and submit them to each core, and the number of particles will be equally divided among the cores. So it will be divided by 12. So if I'm doing, let's say 12 million, then it's going to split, each core is going to actually calculate 1 million. The problem with this approach was, okay, now when people want to expand, so I had a cluster, let's say last year, and this year, now I went to the market, I found actually more powerful CPUs. So I want to expand. Then I got another computer which has, for example, 8 cores or 4 cores, but they're faster. The problem you faced is now, if with the old approach, is if you're splitting. So suppose we had 8 cores with slower machines, and now I have 8 cores with faster machines. And I now want to split the job into 16. The problem you'll face is that the jobs running on the faster machine will finish actually earlier than the jobs running on the slower machines. So what you're doing, you're not actually gaining a lot. Because still you will be restricted. The simulation will be finished when the slowest machine actually finish its particles. With the EXB, it's a new way of actually parallelizing things. Is basically, it does it in a smart way. It has like a basket. So a basket, let's say, of 10 millions. And then each program running on a core will take, let's say, 1,000 of these 10 million and run it and report the results, give the results. Once it's done, it will go and take another 1,000 and so on, okay? So at a given time, it's actually simulating or getting actually a small number of particles or histories. So let's say 1,000, I don't know exactly how this is done, split. This makes sure that the faster machine, they will finish, let's say, the 1,000 faster than the slower machines. And then they will go and grab another 1,000, another. So probably they can grab 4,000 before the slow machine actually grabs another 1,000. So this makes sure that at the end, you will roughly have the simulations running or they finish roughly at the same time. Okay. So by the time that simulation is done, the fast cores could actually do like out of the 16 million, let's say they could actually finish 10 million or 12 million, and the slower cores did only simulation for 4 million. So that's the advantage. Now, the only issue is, as you know, for networking, if you get, because you need to share folders, you need to actually, because with Slurm or when you use it on different machines, they need to write to the same directory, to your home area or the EGS home area. Now, it does not make sense that you actually create or install EGS on each of these machines, because you want a common area where everything is written and so on. So this is like, it's a shared folder. And Windows has that, the Samba, and Linux, they use NFS, network file system, and so on. So what you need to do is then you need to have one single server. This server is actually going to export the home area to all the other machines. You don't need, you need a big hard disk for one machine. The rest, you can just use a 32 gig, something small, does not matter, because home area is going to be shared from that machine. You need to also NIS, that is information system, because you need privileges. Okay, it's a bit of a, it's not simple, it's doable, but then when a machine executes and wants to write to the folder, it needs to have access privilege to access to that. So the users need to be exactly the same with the same user IDs on all machines. You could create users on each machine, or you have with the server what's called an NIS. It's like the Open Directory, I think in Windows, that's what they call it, where you actually create a user in the server, and then all machines, they actually get the information on the server. You need to do that. So it's involved. I wrote actually the steps. The steps were specific for the Raspberry Pi, but these steps with small modifications, you can do it actually on machines or running Ubuntu. No problems at all. Okay, so let's see. Finished. Yeah. So the simulation finished. Okay, and so SQ. Okay. So you see now it's done. Nothing is there. So let's go and see the results. Home, those are Z. Okay. And now I'm going to look at, so I slurm, and let's look at the eggs log file. Okay. So just to show you something. Okay. We did the split of 12. This one, this is the first W1, the first split. Okay, the total CPU time is 235. Okay, and the number is it? Don't have number of cases here. Okay, I think it's in the X list. Fine. Okay, so the next one, the second one, ran on the same. Okay, problem. So everything, all of these jobs, they actually finished within 232 seconds. So less than 5 minutes. Imagine. Okay. Yes, here it is. The number of cases. Okay. The first job actually did a million simulation. The second one, a million. This is 1,000,008. Okay, 1,000,008. Okay, and then we have 1,000,008. This one did only like 400,000. So probably these four, they were running on the Raspberry Pi 3. The lower, the slower machine. But still, everything finished within the same time, roughly 232, 230. So this is the nice thing about this new feature of how they implemented the parallel processing. Okay. What do you mean by fast computers versus slow computer with the same core? Is it, well, if you bought a computer last year and you went and bought another computer this year, you have the CPU, the speed is faster, okay? Or it depends on their specifications. So the simulation, to run the simulation, I just like on the Raspberry Pi 3 and 4, exactly the same job. And it took 3 times more on the Raspberry Pi 3 than on the Raspberry Pi 4. So for a single core. Windows, I don't think you can use it. Windows, the problem is parallel processing. How do you do that? Linux, you can do parallel processing on the same machine, taking advantage of all cores, or you can actually make a cluster of machines where you can actually distribute jobs to run on different machines. So that is doable with Linux. Windows, I don't think you can do that up until now.
You can use it, Dr. Omid, for Windows using Snowfall. Special package is called Snowfall. It do like distribution of the work. This is what they're writing about, the parallel processing for Windows.
So would EGS support that?
I'm not sure.
Okay, so one needs to check. There probably people did it. I'm not saying that it's not there or whatever, but with Linux there is much more documentation, and I mean, I went and for Slurm, I just actually I shared the article. The article was actually for Raspberry Pis. How do you make a cluster for Raspberry Pis? I used exactly the same article. There are small things that I've modified. For example, the shared folder, I actually made it the home area rather than creating a folder, and so small things. And at the office with the Ubuntu machines, I've done it. So there is no problem with that.
Yeah, it's also supported by by EGSnrc, and I shared the document. Some people did it in the Red Edit. It is there. I shared the link for the group.
Yeah. So if you want to do it with Windows, go ahead and do it, and just follow the steps or contact people who have done it and so on. So that's fine. Okay. I've been using the script, okay, for a while now to do parallel runs in Beam. Okay, when creating, able to use using four things. Okay. When I use source, I'm not able to. Okay. Yeah, so you just need people who are interested in doing this for Windows. They need to read more what people have been doing, and like I told you, someone actually used GPUs to actually do a simulation. So people are very creative. Okay, so I don't know if there are any questions, or should we wrap it for today? More about how to continue with the interrupted sync. I told you, you need to create the files. You need to go into these directories, get the files, and then restart. It's basically you need to get.
Yeah, can you hear me?
Yes.
Yeah, actually, what I faced yesterday, actually, I ran a simulation 10 around 1 billion particles, and in between the power off happens.
Yes.
So I lost all the data because of the power off system. So I want to continue.
The data is there. You just need to go. You will going to find this EGS run directories. Go look into them.
Okay.
And the files are there.
I am getting 4 files like EGS that, EGS list, EGS error, and EGS log. So which file
just copy all of them.
in the main directory of that is
Yes. Yeah. So what simulation are you running?
for Beam NRC for different.
Okay. Beam, the phase space files are actually in the main directory.
Okay.
So you see that because you're doing phase space files.
Yes.
Okay. The phase space files, you're going to find them in the main directory. That you shouldn't be worried about.
Okay. So just I have to just change the option
Just
to
just restart. Yeah. Just if X that just what I would do is I would copy first. I would see how many when did this power off happen. Is it like
Okay.
when I've just after 1 million 1 million I would just ignore it and just repeat. Okay, do it again. But was it, for example, did it happen halfway or at the end? And the time and by the way, what's the expected total time of simulation? If the total time of simulation you're expecting this to finish within, let's say, a day, I would just ditch everything and just run it again. But if this is going to be like for 4 days or 5 days,
Yeah,
then
yeah, it was working from last 3 days, and it may take around more 2 days to that simulation.
Yeah. Okay. So what I would suggest is, I don't know how many particles. Why are you running these long simulations? I really don't understand why. But what you can do, the phase space files are still there.
Okay.
You can what you can do now is you can add them and combine them.
Okay.
And see, for example, how many particles you have, because you want phase space files, right?
Yes.
Add the phase space files, okay, and see how many particles you have. Is this enough or not? If it's not enough, then you can actually restart the simulation, so it accumulates more.
Okay.
So look at what has happened when okay, so analyze the situation and then decide, should I run again? Or this sometimes is an issue, because especially if you're running in a cluster where others are actually using it to do calculations, then you have to figure out, do I have enough data to enough or not enough? Okay.
Okay. Thank you. I'll check it out.
Okay. Okay. So anyway, if people who are interested, I know Singh is probably interested, Bilal is interested to build their cluster, then I would advise, if you're not familiar with Linux, get a friend who is familiar with this to help you in doing that. I can send you the instructions, but then you need someone who understands these things, who can edit files and so on. Okay. Okay. So in that case, if there are no more questions, I'm wondering what are the others doing? Like we have Jawahir. I don't know what about the X-ray tube. I see Yahya Amin. He always is present, but I don't know what he's doing. You have to actually start on a project. You have to do something. This is how we can help you. Okay. The assignments that I give you, try to do them. That's, I know this is not a school, but these are just exercises so that it builds your skill. And then suddenly, maybe when you're doing something in the clinic, or you want to do something, you want to investigate something, and then you start, okay, I want to do this project. How could someone help me? How can we do this? How can we do that? Okay, so that's my interest. This is how you learn, actually, how to use EGS better.
Dr. Omid.
Yes.
Yes, there is difference between, because I use Benelux code. So I ask you about the uncertainties that I have it. There are 2 sigma. You know 2 sigma?
In the code?
Yes.
EGS?
No,
or a different code?
The different code.
No, I don't know other codes, to tell you the truth. This is something, you know, I'm an EGS guy, okay? But I know there are other people who use other codes because they have advantages. I think, especially when you do low X-rays, there are more efficient codes than EGS.
But I ask you about, it is the general case. What about the uncertainty? What is the most, يعني, most good, most best uncertainties line? It is under 10%, for example.
No, it depends on what you want to study, okay? Uncertain. For example, like I showed you this case that equivalence and so on. Now, I want to actually reduce the uncertainties while I was running the simulations. Okay, I found them really a bit high. If I'm getting a 1.2% with an uncertainty of 5%, and I want to prove that this is, for example, is equivalent, so the ratio is 1 or not equivalent, then the uncertainty is too high for me to actually come to this conclusion. That's why I need to run additional particles. My suggestion always, people, okay, my suggestion is you start with low number of particles. You do, for example, 1 million, and look at the uncertainties. Is the uncertainty good enough for your study, or you actually need to reduce? You can always reduce uncertainties by just running more particles, but this is not practical. Okay, you cannot run this indefinitely. That's why I have this issue
you
with
can use variance technique. Variance technique is good for that. I use
variance reduction technique is basically, it's a way to reduce to obtain the uncertainty, to reach an uncertainty at a shorter time. That's all what it is. Okay, that's the whole idea of variance reduction technique. Is it doesn't improve your results. It's basically you can reduce your uncertainties in a shorter period of time. That's the whole advantage.
Yes, yes.
Okay, that's why I'm not really too worried about it. If I did not use this, for example, the Bromwich splitting when I do X-ray high energy, or if you're doing low energy X-rays. Okay, if you used 500, if you did the Bromwich splitting 500 or 2000, does it really matter? Okay, at the end in your results, maybe with the 5,000 you can get the results maybe faster. Okay, maybe, I'm not sure. Okay, or maybe it is actually slower. I really don't know. But at the end, you run the simulation, and the important thing is the results. You do the analysis on the results. The variance reduction technique is just a way to get your uncertainties lower faster. That's the whole thing.
Yes. Okay, thanks a lot.
Okay.
If there is a rule to random numbers for that uncertainty, random number that you use it.
A random number, you mean for the
random seeds? Random seeds.
But a seed is just a seed. Has nothing to do with the uncertainties. A seed is just something that begins the simulation. Okay, and as you run the simulation, seeds change and so on. Playing with I like to actually control the seeds, because sometimes there is a bug, and this is, for example, how I can tell the guys at NRC, look, I found this bug, run the simulation with that seed, you should get the bug. And then they see the bug and they see the error, then they modify it. So that's the role of seeds, in my opinion. But that's why I never actually change the seeds. I just leave whatever is there in the file. I don't care about it much.
Okay.
So yeah.
Yes. Okay. Complete, Doctor.
Yeah. My suggestion is, when you ask, okay, this is a question I always, when I started doing simulations, Monte Carlo, is, okay, how long should I run the simulation? Should I run it for a day, 10 days? I really don't know. Then at the end, this is the way I do it. I don't run simulations, indefinitely. I start with 1 million. 1 million is a golden number for me. And I start to see the uncertainties that I get from this 1 million. And does it actually show me, like if I'm looking at fluence or dose, is this enough for what I want to actually study, or do I need to run it more? Then the nice thing is when I do this is then I can actually in my Excel sheet have all link and calculation of like what I have shown. I've actually made the Excel sheet just using the 10 million simulations. I calculated everything, and then I start to say, oh, I need to reduce this, so I need more histories. I need more histories. Okay, so I did it 3 times until I get an answer that convinced me that 10 centimeter in solid water for cobalt is actually equivalent to 10 centimeter in water. It's not 9.5, not 9.6 for that 10 by 10 field. I have to be also specific. Okay.
Okay.
So that's my suggestion. Take it slowly. Singh has a different approach. He goes for 1 billion immediately.
Yeah.
But it's just a way, because it's a waste of I think a waste of resources, because you could actually achieve the same thing with the same conclusion, same, you know, with just a lower number of histories.
Yes. Okay.
Yeah. Okay.
Okay, doctor.
Okay. Okay. So I guess we're at the end. So if you have really a project, you know, just state it, and we'll put you as a and if you want to help in a project, you know, just feel free, so, without any problem.
Inshallah.
Okay.
Inshallah. Okay.
Inshallah. Okay.
Okay. Thank you, Dr. Omid, for all your efforts. Thank you, everybody, for joining us today. And inshallah, we'll see you next week.
Okay. Inshallah. Okay. Assalamu alaikum.